So if you recall, one of the motivations that we had for starting to study projective space was that over the complex numbers, the complex projective space was a compact topological space. And then if you have any projective variety, then, I mean, of course, it's closed inside Pn in the Zariski topology, but I mean, it's just cut out, at least locally on these affine patches by some equations or some continuous maps, which are still continuous in the complex topology. So in fact, X is also closed inside Pn with the complex topology. And then because this is compact, the closed subset of something compact is also compact. So any projective variety in the complex topology is a compact space. Now, what about the Zariski topology? There it turns out that actually every pre-variety is compact with the Zariski topology. So this is a certain exercise here. It has to do with the fact that the open set in Zariski topology are very big. And then somehow if you have any open cover of the space, then the elements are so big that you can always find a finite subcover. And so somehow being compact in the Zariski topology is not such a important feature. Basically everything has this. So we would like here in the following to generalize some other nice properties that compact sets have. In particular, we would like to see some things like the images of compact sets are compact, or closed subsets of something compact are compact, and so on. And the right notion, in particular, if we look at this first property here, is the notion of a closed map, namely map between topological spaces is closed if for any closed subset of the domain, this image is also closed. And for varieties, it turns out that this is actually still a relatively special property, because we have seen, for example, that the images of closed sets don't have to be closed before. And so we want to show that when X is a projective variety, then this actually works out very nicely. Even if the target is any variety, it turns out that any morphism from X to Y is closed. So this shows that the pathological examples that we had before of images of morphisms being some strange things, they cannot happen when the domain is a projective variety. And we start with a special case. And it seems a priori that this is a very special proposition. But in fact, we're going to see as a corollary that this property holds. Okay. And so the proposition says that exactly one type of map is closed, namely just a projection map from Pn cross Pm to Pm. The projection to the second factor is a closed map. Okay. And the proof, as we're going to see, the proof is has a lot of parts. And so you might want to pause at any moment to really think about what is happening, but I'll try to go through it very carefully and slowly. Okay, so we want to show this map here is closed. So we start with Z being closed in here, and then we want later to prove that its projection is closed. First of all, we want to describe this Z better, and then we use what we saw in previous video, that this product here can be embedded by the Zekre embedding in some big projective space with Zekre coordinates Zij. And then this in here is closed, and then we saw this is a closed embedding. So in other words, Z inside this big projective space is a closed subset. And so we can cut it out, first of all, here by some homogeneous equations, F1 up to Fr, in the Zekre coordinates. And then, of course, if we kind of pull these equations back here under the Zekre embedding, then we get some equations which still hold here. I mean, there might be some overkill because actually these were enough to cut it out here, but that's fine. I mean, we still get that the vanishing of all these Fi on here cuts out Z. So in other words, Z is the vanishing locus inside Pn cross Pm. Sorry. of these equations here. And so these are homogeneous in these Zegre coordinates. And then we saw some useful remark before, namely that if you have any projective variety, you can actually cut it out by a system of equations all of the same degree. So you can look this up again. This was this remark here. So we can modify the equations that we have before a bit to all bump them up to the same degree d. So without loss of generality, all these fk are actually homogeneous of the same degree d. And then what this means, I mean, somehow we had the Zegre coordinates here, but the Zegre embedding, this just said that the Zij is equal to xi times yj. That was the formula. And so if we plug these in here, then these homogeneous things of degree d in Zij become bihomogeneous polynomials of degree d, both in the variables xi and the variables xj. So this was the preparation. So we have now cut out z inside here by such bihomogeneous equations. And let me summarize this again on this next page. So z inside here is the vanishing locus of these bihomogeneous degree d equations. And now we come to the actual thing we want to prove, namely we have this projection map to the Pm factor. We want to show pi of z is closed. Okay. And so what we just do is we fix any point in the target and ask the question, is this thing in the image? And we are going to manipulate basically this condition until we reach something which obviously is zariski closed. Okay. And to do that, note that if you plug in some representative of this fixed point A into the second slot of this fi, then, well, you still have the remaining variables x0 up to xn. And then this gi, which you obtain like this, is now a homogeneous polynomial in these variables here. And I mean, you could choose a different representative here, but in any case, these gi would be unique up to scaling, right? And now the condition that we're actually going to manipulate is we're going to ask, is A not in pi of z? That's somehow a bit nicer to think about. So we start here with this equation, A is not in the image, and then we want to prove this is equivalent, after a lot of equivalences, to some zariski open condition on A. And once we have that, we show that this is closed, and then we're done. Okay. So A not being in the image of Z just means there is no point, no preimage point under this projection. So the preimage points looks like this. There is no such point in Z. That's just pretty obvious. But this is equivalent to saying, well, now there's no X in Pn with this condition. So in other words, such X are cut out by the equation that the GIs should be 0, right? Because the FIs cut off Z. And so fixing that the second coordinate must be A, the GIs now cut out the remaining conditions on X. So in other words, this is equivalent to saying that the projective vanishing locus of these GI equations is the empty set. And then by the projective Nullstellensatz, we have characterized this. You know, this is equivalent to saying that, well, this ideal, if we take the radical, then either it is everything or it is this irrelevant ideal. This was written in this proposition here. And so we have transformed it now into a purely algebraic condition. That's good because we want to go to the stage where we can see that it is actually a zariski open condition. And now the claim here is this, this condition here is equivalent to saying that some power of all of these xi is contained in here, right? I mean, somehow x0 being in this radical means some power of x0 is in there, and so on and so forth. And once all the generators of this ideal are in a radical, then also the entire ideal is in a radical. So somehow This here clearly implies this. Note that if this radical is actually everything, then, well, all the xi are actually also in there. You can take ki to be 1. So somehow, this is basically just some manipulation, some rebranding. Okay, and then note that if some power of all the variables is in this ideal, then if you go big enough, if you look at the high enough degree, and the correct degree is that you take the sum over all these powers, once you are so big that you're bigger than the sum of all these ki, then the claim is that actually all monomials of this degree k are contained in this ideal. And the idea there is just that once you are a monomial of this degree here, then one of the xi must appear with power at least ki by some pigeonhole principle, if you want. And then since this thing is in the ideal, then also the entire monomial is in the ideal. Okay, so this is also reformulation, just saying that this entire homogeneous degree k part of this ring is contained in this ideal for some k. Okay, so we have started manipulating this statement with the gi, and now, well, this condition star here, certainly since these here are all homogeneous of degree d, then every element of this ideal is of degree at least d. So clearly this can only happen if d is less or equal to k. So we have to be at least degree d here, and then still we have well, and then we have this kind of equality here that the entire homogeneous degree k part is actually equal to this thing here, because I mean these are just all possible polynomials homogeneous of degree k, and then we write here that this is the homogeneous degree k part of this ideal. Okay? And so then we have that this equality instead of containment as before. And then here, let's look at this ideal. So this spanned by G1 up to GR. So the general element looks like this, H1 times G1 and so on up to HR times GR, where the HI are some polynomial. And then what does it, how can we have such an element which is homogeneous of degree K? Well, the GI are homogeneous of degree D, so the HI must be homogeneous of degree K minus D, right? And then, in fact, the entire degree K part here is parametrized by a certain K-linear map called Fk, which just takes these H1 up to HR, which are homogeneous of degree K minus D, and sends them into here in this degree K part by this map, right? And then the image of this Fk is exactly this degree K part of this ideal. And then this containment here, or this equality here, means that this Fk map is actually a surjective map, that we can reach every homogeneous degree K element by this map. Okay, so we have transformed our original condition A not being in here to this condition that this map Fk is a surjective map for some k greater or equal d. Okay, and now we're starting to be in business, because we have already seen some conditions that being surjective, or that having a certain rank, that these are Zariski open conditions. Namely, Fk being surjective is equivalent to saying that the rank is the rank of the target, right? And the homogeneous degree K part of this ring here, that's a formula you have probably seen a lot of times. This is this n plus k choose k. Okay, so being surjective just means the rank should be equal to this thing. And now we are really in business, because this is a linear map, right? We have seen it's a k-linear map. And so it is described by some matrix. And the matrix, somehow the target has this dimension. So this is the number of rows. And the domain has dimension r times the dimension of this part here. So it's r times this binomial. But in any case, it's just a big matrix a priori. And what are the entries? Well, the entries you see, I mean, this map here is described sending these hi to these linear combinations. So the entries of this matrix just depend on these gi. And in fact, they're just the coefficients of these polynomials. So if you write this down in some basis of monomials, then you just see that the coefficients there are the coefficients of the monomials in the gi. But now we have to remind ourselves, what were these gi again? Well, we scroll up, and then we see the gi were obtained from the really fixed polynomials fi by plugging in these coordinates of a, the point in Pm that we're interested in, into the second coordinate. And so in other words, the coefficients of gi, they are homogeneous polynomials in the coordinates of a inside Pm. Okay. And that's good because in the end, we want to have, if you recall, we're still doing some condition that A should satisfy. Now we identify where does the A come in. It comes in by the coefficients of the gi, in other words, the entries of this matrix. And then this matrix having this rank n plus k choose k is equivalent to saying that one of the maximal minors, so one of the minors of size n plus k choose k of this matrix is non-zero. Right, a matrix has full rank if and only if one of its maximal minors is non-zero. These minors, these determinants of the submatrices, they are homogeneous polynomials in A. And then these not being zero is exactly, it's a risky open condition inside this, inside this, not PA, but inside PM. Exactly. And then we conclude that was what we wanted to show, namely that this set of A such that A is not in pi of Z inside PM is it's a risky open condition. That's what we concluded here by these minors. And so its complement pi of Z is a closed set. Okay. So this was a complicated proof, and I mean, I can recommend that you read through it again carefully, but the upshot, the basic idea was that we took this condition here via the Nullstellensatz, we characterized it in terms of some condition on the generators of this ideal, and then we manipulated it until we had this kind of rank condition on some concrete linear map, and then we could see this rank being maximal is a Zariski open condition. Okay, so that was the rough idea. One remark more generally about this, the type of result that we proved here is that what are now the equations of pi of Z? I mean, if we have that pi of Z is closed, in principle, we must be able to describe the equations of this in these variables, y0 up to ym. And turns out these are exactly the equations in these more variables, which cut out Z and which only depended on these y0 up to ym, right? I mean, if you have an equation which vanishes on the image, then the image of this projection, then I mean it's also, if you add these more variables but don't use them, it's still an equation which vanishes on Z. And conversely, if you have some equation vanishing on Z but not actually using these xi, then it's also an equation cutting out pi of Z. But so this means that what we really did here was we started with a system of equations on Z, and then we eliminated these variables. We tried to find equations which only depended on these things here. And so the proposition that we had before is sometimes also called the main theorem of elimination theory. We got rid of these extra variables, x, xi. Okay, so that was another perspective on what we did here. And now, as a corollary, we get this nice result here, which says that the projection pi from Pn cross y to y is closed for any variety y. So this is more general than we had before. Before we had the case where this was Pm. And we can do it in 2 steps. So first of all, we have that if y inside Am is an affine variety, then, well, we have z closed in here. We want to show its projection to y is it's still closed. But then this here, y sits first of all inside Am, and Am sits inside Pn. And we can do the same equality here. And then we see we get a commutative diagram. We can first go to y and then embed in Pm, or we can first embed these factors here and then project the second factor. And we see this pi prime that is on the right here. This is the map that we know something about. Right? And then we just try to reduce to this known case by saying, well, you start with the z here. What you can do is you can take its closure all the way on the right here. And then by the proposition, we know that if you project by pi prime this closure, then you get something closed in here. And then we just see that taking now the image of pi under this map here, well, first of all, it's the same thing as taking the image. So somehow if you compose with this map to Pm, it's the same thing as composing like this. So we can equivalently see this as sitting inside here and then taking pi prime. So we could write, instead of pi, we could write pi prime. And then the z, because z is closed inside Pn cross y, it's just the same thing as taking the closure here and then intersecting again with this set here. Somehow this is just basic topology nonsense, that somehow if you take the closure and then in the bigger space and then restrict again to the smaller space, you didn't add anything if you were already closed in here. So we have just manipulated it as follows, but then you see Pn cross y is just pi prime inverse of y in here. And then if you look at this equation, we take the pi prime image of something intersected the pi prime pre-image of y. And so taking a pre-image intersecting and then taking image again is the same thing as first taking the image and then intersecting on the target. And then if we look at what we did here, we have written the pi of z as something closed by this, what we had proven before, something closed in here intersected with y. And so it's closed in the relative topology on y. So we get that pi of z is closed inside y. Okay, so here we just basically embedded this into some situation which you already knew, and then we could take the closure and restrict again. And then the second step, now, if you have y any variety, well, the one thing that we know is that it has a cover by affine open sets yi. And then, well, z is closed in this product here. And then you have these nice affine open sets like this, mapping to the yi themselves. And these are now affine. So by step 1, where we know pi of z intersected yi is closed in yi, since being closed can be checked on an open cover. And then since being closed can be checked on an open cover, we can actually, it suffices, if we want to prove that pi of z is closed in y, it suffices to show this for all these intersections with the yi. For those we know it is closed. And so we also know that pi of z is closed in y. Okay, so this was kind of the preparation. And then in the next video, we're actually going to see this results that the image of every projective variety is closed.